Good morning, everybody. Good morning. Let's see here. Let me find my chat. Nah. Mhm. Yeah, there we go. Wait. There we go. Is that the chat? I'm such a doofus. I can't figure any of this out. Let's see here. Wasn't it? No. No. Let's see. Chat. There it is. Good morning, everybody. Well, we got a lot more people today than we did on Tuesday. I wonder what I did wrong on Tuesday, if I did something wrong on Tuesday. I don't really know. I got to start my webcam. There we go. Webcam is started. I mean, I guess I don't know if I mean to complain, maybe. But there's a lot more work that goes into preparing for this online stuff than there is that goes on to an in-person lecture. In person, you can kind of write things down and you know, and then things sort of take care of themselves, you know, because you're there, you can talk to everybody. But oh my gosh. Good morning, everybody. How are we doing?
We're doing great.
Good, wonderful. Oh my gosh. Thursday is like my Friday, because when I'm done teaching on Thursday, I can take a nap. You know, that's like the equivalent of 20 years ago. You know, I don't know what I was doing 20 years ago, to be honest. I know I wasn't partying, but now it's nap time, you know. So, yeah, there's a lot more work, but that's all right. It's fine. Don't care. So, where should we start? That's one thing I didn't really go over. I think I'm going to talk about lab stuff last because, well, I'll talk about it at the beginning and the end. How's that? Oh, I got to do a share now, right? Got to share.
Oh, I have a question, Dr. T. Can you switch me to the Wednesday group first, group A? So next week I will go to lab instead of the 20.
Okay, let me let me check on that. Man, let's see here. So,
I'm in yeah, B. Yes. Can I
so
switch
you want to switch where?
to to Wednesday also, but in February 17.
Oh, you want to switch to the first day in February? Okay,
Yes.
already. Okay, well, how are your car washing skills? Man?
Huh?
How are you? How are your car washing skills?
It's not good.
Not good. Oh no.
House cleaning.
I don't have kids you can watch anymore. I don't have anything. So okay, all right, all right, all right. All right, control X. Hey, there you go. So you will be the February 17th, a Wednesday person in DH10. Good. Yeah. I'm starting to to figure this out. It looks like we're gonna do a combination of either Raman for the first day. I don't know exactly how to put it in. Raman and UV Viz, but I'm not exactly sure which to do in which room.
Dr. Terrell,
Yes.
I was looking at the lab rotations on Canvas and I noticed that my name wasn't on it.
Oh yeah. Okay, so Michael, right?
Yeah.
All right. So how are your house painting skills?
Average, I guess.
Okay, where do you want me to put you? I can put you pretty much. I can put you here, 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 here.
I'm honestly cool with anything, honestly.
Okay, all right. Let's see. I'm going to keep this open, and I'll have one sane day, and I will put you with Van or with Cindy. Yes, I will put you. Well, Wednesday. This is an early one. This is 7:30 a.m. And then this is 9 a.m. You sure you're cool with anything?
9 a.m. actually sounds
9
better.
a.m. All right, all right, all right. So the 18th or the 25th. This gives you more time at the end of the semester.
18th sounds good.
Okay. All right. Excellent. Great. All right. So, alrighty, good. So that's so far so good. Probably our first rotation. You know what? I'm going to do it the opposite way. I'm going to do UV Viz.
Dr. Terrell, I think you actually
Yes.
put Van in that spot again instead of Michael
What?
on February 18th.
February 18th?
Yeah, I think you just put
You
Van.
just pasted, but you had Van's name in on your clipboard.
Yeah.
Oh, God. Okay, hold on. I don't know what's going on. I'm going to have you guys guide me.
So.
Okay, so on the 18th?
Yeah. So.
On the 18th?
So go there.
Yeah, you accidentally put Van again instead of Michael.
Van loves left.
Oh,
so
got
go
it.
twice.
Okay. So it's Michael Wynn, right?
Yeah.
Is that right?
Yeah.
Oops. How do you? Oh, NH, right?
HUYNH.
Okay, not HNH. NH. Right?
Yep.
Excellent. Cool. Got it. I love the name. I just can't spell it. It's like such a, I don't know. Anyway, I know a bunch of wins, but I can't spell the name very well. So I can sometimes. There's Pauline. She's a member of my research group. Her name is Win. But anyway, so where we left off last time was we were talking about UV Viz, and we were talking a little bit about. Oh, you know what I should probably do first is I got a bunch of complaints about the homework, and then I said, what are you lazy students complaining about? Then I looked at it. Oh my God, I assigned too much homework. So I assigned too much homework, but I'll help you a little bit with it, and then I promise never to do it again. Plus, 18B, I already trimmed it down. And plus, I made it due on Monday instead of Friday. So I couldn't change it too much because some people had finished, and that would be sort of douchey of me for them. But I sometimes have to choose between the least douchey alternative. But there were a few questions about this guy. And one of them, so let me grab my webcam here. One of them had to do with this problem from the homework. And oh gosh, so we're measuring iron with thiocyanate. And I'll grab this homework problem here too. So this is, oh God, I'm not going to find it here so easily. So we're measuring iron with thiocyanate, right? And we take, and they set it up kind of strangely, you know. The first time we take 13 mils of a standard, and we add a bunch of crap, and then we add a bunch of excess thiocyanate, which turns it red. The iron 3 thiocyanate is red. They add nitric acid to make it iron 3, da 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 da. And then dilute it to 45 mils, right? And this new concentration of iron gives an unspecified absorbance, right? And then you take 15 mils of standard, 15 mils of a sample, dilute that to 100 mils, 15 mils of a standard, add the thiocyanate, dilute that to 100 mils, and then that guy, you have to adjust the path length. Now, I have never seen such a spectrometer where you can freely adjust the path length, but I guess they exist, right? So I'm sorry, I should not have given this problem. It's kind of weird, right? But this A prime sample is equal to the same epsilon value, right? Times 3.31 times the C prime of the sample, which is the unknown sample concentration, right? And this will equal, so this is epsilon B C prime standard. So this is the same thing up here, right? A prime standard equals A prime sample. And I'm priming him because I'm trying to remind myself that this is for a diluted sample and a diluted standard, right? And I guess the beauty of this is that you can cancel the epsilon value, right? So you got epsilon BC equals epsilon BC, right? We can cancel the epsilons, and we've got one equation and one unknown, which is C prime sample. Right? C prime standard is C0 standard times 13 over 45. That's the dilution factor on that guy, right? And then, at least in the iteration of the homework that I did, it was 13 and 45 mils. You got to watch that because they change the numbers, right? And so that C prime standard is C0 times 13 over 45, which is 5.37 times 10 minus 4 molar times 13 over 45. That's equal to 3 C15 over 100. And you simply solve for C prime or C0 sample. And this came out for me. It took me a couple tries. I think I messed it up once and maybe again, I can't remember. But this is what it came out to be. So is this helpful to anybody? I gotta get some sort of clue here. Where is
Yes, it's
the?
helpful. Thank
Oh,
you.
good. Thank you. Thank you. Thank you. Thank you. Yeah, people are getting better at waking up, and it's
I
a
have a
good
question,
thing.
Doctor.
Yes, so
For homework 18B, I was looking at it. Could you please take away question 21 and question 31? Because those are too hard. Or
21
could
and
you,
21
yeah.
and 31 are too hard.
Yeah,
Oh.
I just don't get it because I was looking at it because I was gonna start it later on today and I don't understand.
Okay, so what are you willing to do to make me give up 21 and 31? That is the question.
Buy some cake. Do you want red velvet?
Cake? Oh God, no. I'm fat and I'm 50. I'm 57 and I'm fat.
Isn't he already washing your car, Terrell?
Oh yeah, he's just gonna live here. I think he's just gonna live here. Yeah. How are you with that? Can you live in the front yard, Solomon?
Yeah, I can make it work.
I'll put a tent up for you.
Thanks.
Okay. Okay, hold on. Let me see this. I tell you what, let me jot those numbers down and I will either omit them or I'll clarify them for you. Okay. So which numbers were they?
21 and 31 on homework number
21 and
18.
31.
Yeah.
You know, it's so strange because I don't get them numbered when I go to that website.
Oh.
It's really weird.
31 is the last one.
Oh, the last one? This is the
Yeah.
last one. Okay. And then the 10th from the last. Okay.
Is
Okay,
it
so let's,
correct?
yeah. Yeah, you looked at them too, Van? Good.
No, because I'm in the Western 18, so I think I'm in the middle of it.
You're in the middle? Oh, you're working on 18. You're working on 18A or 18B? Yeah,
18B.
you're working on 18B? Let's see if they number them here for me. Oh yeah, they're numbered. They're numbered. Okay, so let's see here. Oh, but see, there's only 19 left, right?
Oh, okay. Last time
Yeah,
it was
so-
question
so-
31.
Yeah, so I cut it way down already, evidently.
Thank you so much. Because
Well, you don't know if I took away the ones you don't like. I
Yeah,
may have left them,
but-
you know?
Okay.
Don't thank me yet. So let's see. But it's probable that I did. There was a whole kind of subsection that I took out. There's fluorescence vocabulary, emission wavelength, and mass of quinine. So I don't think any of those gave you trouble, did they? Solomon?
No, not too much.
Not too much. Oh, okay, good. And
But it's-
then 21, I don't know what that one that might have been. Okay, so I'm going to consider this done. And if you find in the new homework set that it's still has problems, let me know and I'll see what I can do.
Yes, sir. Thank you, doctor.
Oh yeah. Oh yeah. Okay, so here's 18A. So okay, so let's go back to the notes. And here is another one. This one was a little tricky, right? This one was this indophenol. And see, this is quantitative chem, and then what the course title is actually instrumental analysis, right? And so it's a little bit, not quite right for the course description, but anyway, it's all chemistry. It's probably what you probably need this more than instrumental anyways. So indophenol, right? They take, and it's basically to measure ammonia, right? And you add phenol and hypochlorite, excess phenol and excess hypochlorite, and then they'll react with the ammonia to make this blue product here, right? And what they did was they did a blank corrected internal standards. So, no, a blank corrected standard addition, sorry. blank corrected, meaning that you have 10 mils of DI water plus phenol hypochlorite, right? And that gave a small absorbance. And then you have a standard addition where in each case, you're taking 10 mils of sample with some unknown ammonia concentration, right? 5 mils of phenol, 2 mils of hypochlorite, and then diluting everything to 25. Oh, I see. And then, and in this case, you also had 2.5 mils of 5.5 times 10 minus 4 molar ammonia, and then dilute this all to 25 mils. And when I say dilute to mark, I'm going to use the abbreviation QS, which I just learned this last summer, means satisfactory quantity. It's some Latin thing, but it means enough to make 25 mils, right? So this is diluted to 25 mils, right? I don't know why they use QS, but I think it's kind of cool. So we're going to use QS. And then, so these three samples, A, B, and C, they give 0.362, 0.609, 0.045 absorbances. And I went ahead, right? And I blank corrected these. I took 0.362 minus 0.045 is 0.317, et cetera, right? Now this won't matter here when I calculate delta A, because this will get subtracted out anyways. But anyway, so it's 0.247 is the delta A, right? And this delta A is the difference between the standard only and the standard plus sample. I'm sorry. The sample only and the sample plus standard. I misspoke there. So this has sample only. This has sample plus standard. Then when you subtract those two, the absorbance is 0.247. And then and you can use that delta A as the net absorbance for this 2.5 mils of this amount of ammonia, 2.5 mils of 5.5 times 10 minus 4 molar ammonia. So we've got, so this is epsilon equals A over B times C, right? Now there's the concentration of the stock, and this is the diluted stock, right? So what's actually doing the absorbing is this stuff diluted by 10, right? 2.5 over 20. So this gave the right answer here for this part. 4491 per molar per centimeter. And then now we can take the sample only, right? Blank correct it. So it's 0.362 minus 0.045 here. Right, take the sample, blank correct it. We get 0.317. And that is equal to epsilon B times C prime, which is the diluted form of the, is this ammonia? I forget. Yeah, ammonia in the sample, right? And then this is 25 mils diluted to 10. So this is This is C times V equals C times V. So this is, I don't know, I guess I'm just kind of like losing it here. So this is the diluted concentration. Multiply that by 25. And that will equal C0 times 10. And this is equal to 1.76 times 10 minus 4. So this worked out for me too. Good. Can I move on? Not like leave, but are you guys done with this slide? Are you even there? Yeah, I can still see people. I see a thumb up. I have 2 monitors and it's never enough. Okay, so good. Okay, so I think I'm gonna move forward now. Good. Casey, are you done? Almost? Okay, great. Yeah, because Casey, you're like doing next week's homework. So, Kareem, you okay? Everybody okay? Nicholas, Paige, Karen, good?
Yeah, I'm good.
Okay, cool. So, now I wanted also to show I think it's this one. Yeah, hold on. There we go. So there was on the homework set a problem which I cannot find anymore. And it had some calibration, but then the idea was that you should plot it and see that the slope changes for these last 2 points, right? Or say the last 3 points, right? And in that case, what you want to do is you want to get the slope only for the first 5 points. 1, 2, 3, 4, 5, right? This is a negative deviation. And that's really all there is to that one, I think. I mean, I don't remember. I looked back and I said, where is that problem? Because I got questions about it, but
Number 29.
number 29, I am really sorry. I can't find it in my stupid thing anymore. Maybe I should look. But anyway, this is the hang up, is you have to just take the first 5 points, right? And if you take the slope, you can use the equal slope function there in Excel, and you can get the slope. This is y, that's x, It's super easy, and that will make it work, I hope. And then there was a wicked problem at the end. Okay, I'm waiting. It's actually really helpful when people leave their cameras on, because I can kind of see like a little bit of activity. I know people are like writing or something, but if it's just your name and a picture, then, oh, thank you, Van. Thank you. I've got Cindy, Casey, and Van, and they all have their cameras on. Yay. Okay.
Madly scribbling away. We're doing
Yes. Yes, madly scribbling. Okay, so I'm going to move forward now. Yeah. I look like that. Taryn, that's okay. That's okay.
They say, how many people have their cameras off because they don't want us to see the
Right.
breakfast?
It's like that's okay. That's fine. I don't mind. I'm just celebrating those who can. So now here is another problem, and this is a DNA calibration. Let me look at this one. This is the last problem in this set, I think.
The numbers are right on the left.
The numbers are right on the labs.
They're right on the left.
Yeah, I know that. I'm just stupid. I'm sorry. I just anyway. Okay, so here's where we are. This is, it's like, I looked at it, but I didn't realize there was so much to it. Oh my God. But okay, so it's a big old serial problem, right? So we just got to break it down, right? So first we draw a graph and add a trend line or get the statistics for the graph, right? Determine the slope and intercept and the standard uncertainties in the slope and intercept. I don't know, how are you supposed to get that from the trend line, but maybe that works nowadays, right? So that is basically involves just taking the concentration and the absorbance and just plotting them here, you know. So this plot here is these data, right? And then this is also for these data, right? This is the linest. I should type linest. And actually I can also do it like this. Formula text. Just pick one of those guys. And so this is the formula here is called linest, right? And it gives you a lot of crap you never need, but basically it gives you the slope and the uncertainty and the intercept and the uncertainty. And this is so there's a slope and the slope uncertainty. I'll make a quick point about this and then I'll move forward. The uncertainty here has two sig figs, right? Has two significant figures. And here it has two sig figs, right? And it's actually pretty much okay always to include two sig figs in the uncertainty. I mean, we can have a deep conversation about it sometime, but for our purposes, I think it's always okay to have two sig figs in the uncertainty, right? That means that the last digit in the uncertainty is the last digit in the number you report, right? So 0.0097, 0.0045, you know, or 0.0064, 0.02981, right? So that's one way to do that. It's just sort of like, it's a simple rule and it always works, like 99.99% of the time. But so that's good enough for me. So now you can see here that the data are linear, more or less, and we can talk about that more, but there's the slope and the intercept, right? Now here's the slope and this slope here has units, right? It has slopes of, this is the concentration in micrograms per milliliter, right? Stretch that guy out. So the slope, the X value has micrograms per mil. So the slope has 1 over that in terms of its units, right? So the slope has units of micrograms per mil per centimeter because this is a 1 centimeter absorbance thing. So here's the units on that value, 0.02981, and there's the units, right? Then what we want to do is we want to create a molar, change the units here to the slope in per molar per centimeter, right? So we're going to transform this into moles per liter. So the first one is micrograms per mil, right? And here's the microgram unit, right? So we've got to multiply this by the formula weight. And the formula weight was 4568 grams per mole. 4568 grams per mole, right? And I'm just going to say, if it's 4568 grams per mole, it's also 4568 micrograms per micromole, right? So I'm just going to multiply that out. That'll cancel the micrograms, right? Then I'm going to multiply by 10 to the 6 micromoles per mole. That'll cancel the micromoles, but I'll leave us with moles, right? And then take away the milliliters by multiplying by 1 liter per 1,000 mils, and we get this. This is our new extinction coefficient. This is our epsilon value. Oops. Right. And now let's see here. So this is a complete answer. There's no more to this point, right? But now they sort of change around on us and they say there were 2 experiments done with different instruments, both in triplicate, right? And they say first one got 0.019, second one got 0.0145 in terms of the standard deviations, right? And the first question they asked was, what is the corresponding F value for this difference in standard deviation? So this is just the quotient there, 15 over 0.02. You set it up so that it's greater than 1, 0.15 over 0.02, and then you square that guy, and that comes out to 58, right? So this is called FEXP, F experimental, right? I'm going to subscript that, right? FEXP is 58, right? Then you can look up F critical in a table. And you use 2 degrees of freedom, comma, 2 degrees of freedom. So it's the F table and it's in the book here. I think I can show you where this is. Here we go. F table. This came out. This is different now, but the F table here is in this table, right? You just click that puppy. It brings up a table, and then the F for 2 and 2 degrees of freedom, 2 degrees of freedom. Comparing S1 and S2 is 39. So, whoopie-doo. Yay. Okay. So, so back here, right? And so we could just see that the difference in this result is this is a significant difference, right? So that, well, the fact that F critical is less than F experimental, this means that the difference is significant, right? So it's because, oops. So this is basically the answer for this one. It's just that there's a bigger, there's this difference is significant. And then they say, okay, well, what if you used 0.027 instead of 0.0298? How different would the result be, right? And the answer there is then it would be 9% different, right? And this is actually correct too. So you just take the difference in slopes and divide, and you percentage them out. So I don't know if it's different if you take 0.027 minus 0.0298 and divide by 0.027. I'm not sure. I just don't really care. So, but this is a 9% difference in slopes. And then lastly is a hard bit where they say, okay, here's two answers that we got. And we're supposed to say whether there's a significant difference between 8.25 and 8.38. And these are DNA concentrations here, right? So 8.25, 0.019, this is the sigma, right? And here's the number of degrees, or the number of samples taken, right? So the 0.019 and 0.145, these were used up here. I should put the sig figs back there, right? These were used up here, and we got that the difference is significant, right? So what that means is that we have to use a type 2B t-test, right? There's two different types of t-tests you can use. There's a type 1 where you're just testing against the known. Then there's a type 2A where you're testing two values with similar standard deviations. And then there's a 2B where you're testing two values with different standard deviations. And in 2B, you actually have to calculate the degrees of freedom. So that's what I did here, right? You can see that it's just a big ugly aggregate of S and N, S1 squared over N1, S2 squared over N2, the whole thing squared over S1 squared over N1, like this, right? And then you get this, and then T calculated is the absolute value of the difference, right, over the square root of S1 squared over N1, S2 squared over N2, right? And this is all fairly straightforward. The only place this degrees of freedom comes in here is finding basically the T value. Instead of using a table, I use T inverse here. And 0.05, and I use 2, since this came out to 2.07. I use 2.0, and that's close enough. And I don't even know if you're allowed to use non-integers there. I really don't know. But clearly, the T table is much larger than the T calculated, right? And so for all of this confusion here, or this potential confusion, the fact that T calculated, which is proportional to the difference in the answers, is less than T tabulated means that there's not a significant difference. This difference is smaller than this one, right? This is smaller than this. So there's not a significant difference. So yes, they're not different. So the answers that they got using those two methods are the same. Is that okay? Is anyone gonna try to kill me now? Okay, thank you guys. Thank you. I'm seeing like thumbs and crying emojis and all this other weird stuff. So um so obviously I could never ever put a similar difficulty problem on an exam. I just could not even get close to it. This would take an entire hour just to do this one problem, you know? And then I would have like uh I have no time to do anything else. So um anyway, I
We
apologize
could
for
take
the
some of the crying emojis off. It's
yeah,
not so bad.
exactly. Yeah, exactly. Yeah. So yeah, I'm sorry. So uh, okay, so that's actually all I have for the homework and whatnot. And uh, what I'd like to do is just give you guys a couple minutes of break, and then I'm going to come back and we'll talk a little bit more about absorbance and we'll get into luminescence a bit and whatnot. So yeah, it's just a very extensive chapter. There's 130 slides here, and they're all relevant. So I'm going to try and touch on all of it. So um, I will give you a couple of minutes. Oops, sorry. I'm not supposed to do that. I'll give you a couple minutes, and then you guys can uh, take a little break, and I'll take a little break. Then I'll be back at 8:20 or 8:21. How's that? Hello, everybody. I'm back. Okay,
So are we.
so now on to PowerPoint drama.
Aw.
How's everybody doing? Okay?
Yes. Okay. We're doing okay.
Good, good.
Dr. T.
Excellent. All righty. So, here, this is the theory behind absorption, right? And then Harris goes on to make some crazy claims about it, which are just not true, I think. But anyway, first of all, it's like, why does absorbance work the way it does? Why is it logarithmic? You know, why is it the log of the transmittance that's proportional to the concentration? Well, this is a classic sort of a gambit here, right? We're going to show you a derivation, and I, for one, am never going to ask you to do this derivation. So you can just sit back and flip me the finger and listen, because I'm never going to ask you to do this. But I will go through it because it's calculus, and they made me take calculus, and I almost never ever use it. But here's an example where we could sort of use it. So enjoy. So if you take the absorbing solution, right, and you take a thin slice of it, then the light power entering the slice and leaving the slice differ by an amount dp over a distance dx, right? And the dp is equal to beta, some proportionality, and it's a negative, right? Times p times concentration times dx, right? So this is the differential equation, dp and dx, right? So so basically you just rearrange that. Dp over p is equal to minus bc dx. You integrate the left side over p and the right side over b. Why can you do that? Because x starts at 0 and goes to b, and p starts at p and goes to, or starts at p0 and goes to p, right? Beginning and ending values for power and distance correspond, right? So the integral here is log, and then this is just a bcx, right? So, or beta cx, right? So the natural log here, log p minus log p0 is equal to beta c, b minus beta c 0. You just rearrange this, and then you get minus log of p over p0 is equal to beta cb, right? And then you just take the base 10 log, which is 2.303 times the natural log, and you get this transformation. Yay! We have just derived Beer's law, so it's time to have a beer. Yay! Okay, so so this is Beer's law. I mean, I don't know why that takes a whole page to put in the factor of 2.303, but okay. So now here, this slide, I think is wrong. I actually think it is crazy and wrong. I could be wrong, but I think it's wrong. So optically thin, right, and optically thick, right? I think that this just means that if you linearize this thing, you can linearize any function, right? So this is sort of like duh, you know, you can sort of make this case for anything. But the thing is that, like, they say it has to do with a shadowing effect. And it's just not true. I just don't know where they get that shit. I don't believe it. It's like, what's the difference between low absorption and shadowing? Eight a.m. beer equals the move. Yeah, oatmeal stout. I like that. I like that. So I don't trust this slide. It's kind of strange. Why should it be controversial? But anyway, but basically, you just if you keep the absorbance between say 0.001, right, and 2, then you're going to be fine. And just look at it. If it's noisy, then don't use it. Oops. Okay, so let's just take the rest of this today, and we're just going to look at colors and things like that. It's not super crucial, so you can kind of go to sleep now if you need to. But this is, I understand that there's a way to make a color wheel, and I would be open to that. Anybody could show me a color wheel, but there's absorbed and observed, right? So if it absorbs in the violet, it turns out to be green. It looks green to our eye, right? And there's this correspondence, right? It's funny how if it absorbs in the violet, it's green. If it absorbs in the red, it's green, It's like, wait a minute, that's the opposite end of the spectrum. But anyway, I don't know if it looks different to the eye or not. But you can make a spectrometer here. I've actually done this, but I don't know. It wasn't so satisfying to me. And I've tried to use microcontrollers and CCD chips and do this, but I just haven't been successful yet. So I'll let you know when that works. But the idea here, I don't know what it is about having an entrance slit like this, but somehow that makes it such that when it hits the grating, there's a correspondence between the wavelength and the position on the detector. So so for example, if you put white light in to this spectrometer thing, you'll see, violet, blue, green, orange, red, And the reason that you can see this is because the color detector on the CCD is reproducing the spectral qualities in the color simulator of the display, right? That's kind of cool, right? So you have a visual cue as to the wavelength, right? And then if you put dichromate in, which is this orange solution, right? You can see that the dichromate absorbs in the violet here. And it allows the green, orange, and red, green, yellow, orange, and red to pass. And you can see them there. It's kind of cool, right? Then rhodamine 6G, it has a big absorption right in the middle of the spectrum, right in the blue. So this is a cool kind of a reddish color. Same with phenolphthalein, right? It has a bigger chunk that it takes out. Then bromophenol blue absorbs in the green and also looks like in the violet as well here, right? Bromophenol blue, right? It looks like it has also an absorption in the violet, but it's not shown here in this spectrum because you can see here that the spectrometer was getting noisy, right? So they couldn't rely on these values to create an absorption. So let's answer this question. Does the absorbance peak represent colors that are lost in the transmitted visible spectrum or colors that persist. So absorbance, oops, sorry, oops. I don't know if I gave it away there. Absorbance is colors that are lost or colors that persist. What do you think, folk?
Hello. What's the question again, Dr. Teo? Does the absorbent peaks represent colors that are lost?
Colors that are lost or colors that persist? I think it's colors that are lost, right? Because that is, absorbance is what is removed from the spectrum. Yay. Okay. Should we do this? I should probably try to do this. See if I can get my phone to display.
Oh,
okay. So anyway, so here's some different colors. Cool. Oh, I see. And these are actually all silver nanoparticles. And they're different, probably different, just different sizes. And there's an interesting optical effect. And these silver particles, they absorb at different wavelengths, but it's due to their interaction of the collective electrons in the stable, in the silver nanoparticles that interact with light in different ways. And it's kind of, I actually studied it for a long time, but I still don't get it. It's buried in this complex number math. But anyhow, so you can, for larger particles in like A, you can see that they have, this big band out at 800, so they come out green. And then the super small particles look yellow because all their absorbance is around 400. And I'm not sure, this could be a mixture, or this could be rods, rod-like shapes. But anyway, there's different shapes and sizes that give these colors. So measuring absorption, silica is normally used, and silica or quartz is good for ultraviolet and visible, right? Glass or plastic is suitable for visible. Right? Oops. So visible spectroscopy, there's a good rule there. If you can't see it, the spectrometer can't see it. If you're talking about visible spectroscopy. However, if you have silica, then you have to be much, much more careful, because things that you can't see could very likely obscure the spectrum. So ultraviolet is tricky. Okay. And then glass is cheap, but to get from 190 to 340, you have to pay a lot more for quartz. And they're like maybe $20 to $40 for a cuvette. So it's actually, it's fairly significant, Then you can get these disposable ones. Kind of crazy, huh? Cyclic olefin. So one of the things about this upper end of this range is most UV vis machines. Yeah, most of the UV vis machines, they only go out to like 1,000, maybe 1,100 nanometers, and some cut off at 900. So these are, so long as your solvent doesn't kill them, these are fine on the red end, right? The red end is the long wavelength end. But the blue end, they're somewhat compromised. They're like glass, or they could be a little bit better than glass, This guy here is interesting, huh? Cyclic olefin copolymer. I'm not really sure what that would look like, but in any case, it goes down to 220. It's probably some. No,
Okay.
cyclic olefin is not like benzene because
Oh.
an olefin is a single double bond, right? And polystyrene is the polymer of benzene. You know, it has a benzene with a vinyl group hanging off the end. And that actually the benzenes absorb right around in the middle, the mid UV. A copolymer is a polymer that's formed between two different monomers, right? So a copolymer could be styrene butadiene, or I don't know, other things, you know, where there's a couple of monomeric groups which can polymerize together. And that is all I know about that. Consult Dr. Smoko. So here is infrared windows, right? So sodium chloride says it goes up to 700. I think it probably, if you polished it well, you could get it into the visible. KBr goes to 400 and all the way out to 33,000. Oh, I'm sorry. These are wave numbers. So, right. So 33,000 is mid-visible. 28, 30, these are mid-visible, right? But then you can go chloride, bromide, and iodide, right? Sodium, potassium, and cesium. And as the mass of these puppies increases, the frequency, the reddest frequency that you can get through it, decreases as well. So the spectral window improves as the elements get heavier here, right? So this is probably like well, cesium iodide is a very good window material, right? It seems like the very, very best one is diamond, however, right? 45,000, that's in the ultraviolet. 45,000 to 10 wave numbers, geez. You can have trouble measuring that, you know? Polyethylene is transparent down to 10, but only up to 600 wave numbers. And sapphire has a very good ultraviolet window. So let's figure out what the what the ultraviolet end of these materials is. Oh my God. Do you guys know who Gina Carano is?
No.
Yeah.
Gina Carano. Yeah, Cindy?
You guys been watching The Mandalorian?
Oh, I think
If-
you're muted here. I'm going to unmute you. There you go.
Oh, there we go. Yeah, so you guys have been watching The Mandalorian?
Oh my God. Oh my God. I don't have my headset in. Oh, geez. I forgot.
Hi.
I'm so sorry. I haven't heard
you can
anything.
Hear us now.
I can
Really?
hear
See,
you
I thought
now.
I was.
Oh my gosh. Oh my gosh. Oh my gosh. Oh my gosh.
Like, wait, is my mute unmute signal
I know it did. It was like
reversed?
that. It's not working. What's wrong? You know, it's like, no, put your headphones in.
You didn't hear
Oh,
my
God.
answer before?
No, Folk, I didn't get your question.
Wait, you didn't hear my answer before to your questions? No, right?
No, I didn't hear anything. You were just screaming into the void. Although your
we heard you.
Yeah. Your classmates heard you.
Please don't think that I'm disrespectful. I answered. I just don't know the answer to the question until you answer them. I wasn't sure. That was my answer. I wasn't sure about the question.
Huh. Okay.
Please,
Alrighty.
please don't think I'm disrespectful.
Okay.
I was answering the
Well,
question.
I think we should give folk a collective spanking here, shouldn't we? Would that be fun?
I don't know. Fook's not the one who forgot to put his headset in.
Right, that's right. Probably I deserve it. Oh my god. Okay. So anyway, lots of fun here. But so I was just saying that Gina Carano, she played in The Mandalorian, right? And I splurged and I got Disney Plus. And The Mandalorian was kind of a fun series. And she's very big in it. And she came from MMA, right? From mixed martial arts. So she's kind of like a badass, kind of a bonehead though. You know? And I love her. You know, I think she's great in the film. She's perfect, you know. She knows Kung Fu. Excellent. So, but she had all these weird anti-vax things she was like tweeting anti-vax stuff, you know, and I don't know, probably like kill Obama or something weird like that, you know, some crazy stuff, you know. And now they've dropped her from Disney Plus. I'm sad about that because she was kind of cool in that role. But anyway, that's going to be a big loss, I'm afraid. But anyway, okay. So let me see what 45,000 is 222 nanometers. This is 222 nanometers to like a bazillion nanometers. And then 66,000. Let's see here. And that's to 1 million nanometers. Right? That crazy, Diamond? Let's see here. Make this smaller. And then Sapphire is almost as good, not quite. 66,000 is 151. Whoa, 151 nanometers. Wow. And that's to 5,000 nanometers. So anyway, just putting a little more context on this. I don't know, guys. I don't know what I'm doing here. So that's probably enough for today. We can talk about other stuff on Tuesday. I may have to push back the homework a little bit more, but definitely do the homework A for Monday night though.
Can you please push the homework back, Dr. Terrell?
I pushed it to Monday. Is Monday not good enough?
I think like Friday would be good.
No,
Like an
Monday's
extra-
good.
No.
Bro. Monday's
Oh.
a good day. That's fine.
Okay.
Okay. So who wants it pushed back?
Please.
Wait,
Folk
when you say
wants it-
push back, do you mean like sooner or later?
Oh, like later. Who wants it pushed? Like right now, it's due Monday.
I think Monday's fine.
Okay, Solomon thinks Monday's fine. Who thinks Monday is not fine? Speak up. Speak up.
Later, please. Later, please.
Later. Fuchs says later. Who says both says later? Oh, he's not saying now. It was a guy.
It was me, but if people collectively are okay with Monday, then I'm good with that too.
Oh yeah. I suggest we have a cage match between Kareem and Fook.
I'm looking at it this way. The longer we push this assignment back, the more work we're going to have to turn in at the same time.
Oh,
That's
yeah.
true.
Wait.
Because then we're going to end up on top of
That's
other
true.
stuff then.
That's true. That's true. That's true.
Wait, this wouldn't
yeah,
shift everything back?
Yes.
Oh.
Yeah.
We'll
No,
extend
no, 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 no,
it
no,
for a couple
It's
no, no,
months.
no.
Just leave it at
No,
Monday.
no.
Let it go.
No, 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 no.
Leave
no,
it
no.
at Monday.
No,
Goodness
no, no. Actually, I am going to leave it at Monday since there's a reason that it's not a real democracy here. And one of those reasons is I've got to push a little bit. And so I'm going to leave it due Monday night. And it's not that bad. It's not that bad. But if you have like, sometimes it's just such a hateful process to work, and to make yourself work. And I get that, right? So just let me know if and we can work something out, I promise. I have dirty cars, I have yard work to do, so don't worry. We can work something out. But yeah, it's due Monday. Monday is okay. Monday. Okay, good. So Fulk, I'm going to work on your thing here also as soon as we get offline.
Dr. Terrell?
Yes.
Sorry.
Yes,
Can you
no,
please
no.
explain the lab that's going to be for next week?
Oh God.
Oh, yeah.
Oh yeah, there's lab next week. Where?
That's
where
right. That's right.
How-
That's right.
How long is the lab, Dr. Terrell?
So
It will take
the
practically-
lab should take no more than a week.
Okay.
Like 8 hours a day times 7 days.
Wait, what? Wait, that's 56 hours per week.
I'm just kidding. No, the lab will finish everything within the 3 hours that we're there. And so I will send out an abbreviated UV Viz and an abbreviated Raman sort of worksheet for y'all, because we can't do the whole full-blown experiments.
Oh, okay.
And so don't worry. If you are Adam, Mina, or C Bento, or P Riley, or J Little, or K Chiasa, then I'll send out these things for you for Tuesday. Okay, I promise. And don't even worry about it. Don't even worry about it. Even if you don't study it, it'll be fine. I will walk you through. Okie doke?
So we're not going to be doing whatever's in the lab manuals or.
No.
Okay.
I mean, you will. We will. We'll be doing
We'll do
but very abbreviated.
Okay, but like reading it in detail and planning stuff out is not going to help me.
No. I'm sorry. That will only frustrate me and
Okay.
everybody. So thank you.
Then I
thank
won't do
you.
that.
Yeah. Sorry. Yeah. Don't do that. Mhm.
Dr.
Okay,
T,
guys. Yes. Sir.
what time do we have to show up for the lab?
Oh, so on Tuesday you have to show up at 9 a.m. right? So that means that you will probably miss lecture. If you want to, you can come into lab at 7:30 and sit on one of those miserable stools for an hour and a half, and you can do it that way. That's totally fine. Or you can sit in your car, or you can, however you want to do it, that's totally fine. But I just have a quick transition there. So I'm going to go into lab. I'm going to go into my office, do the lecture, then go across the hall and do the lab. And so there will be some weirdness for y'all when you have lab that day, that Tuesday or Thursday. So you can always catch the YouTube. You can bring the views up on my videos from 5 to maybe 7 or something.
All right, no problem. Will do.
All right, excellent.
Dr. T, can we go into the building and
Yes, you can.
watching the video, the lecture?
Yes, absolutely. Yes, you can. Yes.
So if I can I go in 7:30 and
Yes.
or 7:20 and watch the lecture online?
Yes.
And after that, we have the lab.
Yes. Yes, you can do that. Yes. Yes, you can. All right. Okie dokie. I will see everybody next week. Bye-bye.
Right.
Thank you. Bye bye.
Thank
Thank you,
you.
Dr.
Bye-bye.
Nice weekend, Dr. T.
Thank you.
Dr. T.
Thanks
Thank you.
everybody.
Thank you,
Bye-bye.
Dr. T. Have a good one.
Focus
Thank you guys. Thank you.